Okay, let's unpack this. Imagine grappling with a computational problem so vast, I mean so incredibly complex, that the fastest supercomputers today would take, what was it, 10 septillion years to even make a dent. Now, picture this new chip that claims it can solve that same problem in just 5 minutes. It sounds almost unbelievable, right?
It really does. And what's truly remarkable here is that we're talking about Google's latest quantum computing chip. It's codenamed Willow. And, this isn't science fiction. It's a very real development unveiled just a few months back, December 2024. BBC News covered it. So yeah, our deep dive today is all about getting under the hood of Willow. What is it? What does it actually mean for the future of computing? And importantly, where's the line between a real, genuine breakthrough and, well, maybe a bit of the hype that always comes with these things?
Exactly. Our mission today is to get past those big headlines. We're digging into the details from that BBC News piece. Google unveils mind-boggling quantum computing chip. We want to pull out the most important insights for you. We'll look at what makes quantum computers so different fundamentally, what this Willow chip actually managed to do, and crucially what other experts are saying about how significant it really is. Ready to dive in. So to really get Willow's significance, maybe we should start at the beginning. What is quantum computing? We hear the term all the time. But for someone keeping up with this space, what's actually going on under the hood that makes it potentially so, well, mind-bogglingly powerful?
Yeah, that's a key question, isn't it? For anyone interested in where computing is headed, unlike the classical computers we use every day, the ones based on bits being either 0 or 1, quantum computers operate on totally different principles. We're talking quantum mechanics. They use qubits. That's the basic unit. And what makes qubits so powerful is their ability to be in multiple states at once. That's superposition. And they can also be linked together, entangled, even over distances. These weird quantum properties let them process just vast amounts of information in parallel. It completely changes the game for certain types of complex problems.
Right. That distinction really brings the potential into focus. So if these machines work so differently, what are the really exciting applications? What could they actually do for us? And maybe are there downsides, concerns we should know about?
If we look at the bigger picture, the hope is that quantum computers could massively speed up things that are just, well, impossible for today's machines. Imagine creating new medicines, new materials, like super fast, or designing more efficient fusion reactors, maybe better car batteries, even optimizing really complex logistics. Think about shipping routes, or energy grids, telecom signals. Hartmut Neven, he leads Google's quantum AI lab, calls himself the chief optimist, which is quite telling. He expects Willow will see some practical use, especially for simulating quantum systems, though he still thinks broader commercial applications are probably towards the end of the decade. But, like you said, concerns. With powerful tech, there are always dual-use worries. The BBC article specifically mentions fears about breaking encryption, certain types anyway, which is exactly why Apple, back in February, announced they're making iMessage quantum-proof, trying to protect chats from future quantum attacks.
Okay, so Google's Willow chip enters this high-stakes race. Beyond just being fast, what's its main contribution? What's the specific innovation that's got people talking?
Well, the core thing here. While Mr. Neven does call Willow the best quantum processor built to date, it's really a significant step forward, and Professor Alan Woodward at Surrey University points this out. It's actually an error correction. That's the big one. See, historically, a massive headache with quantum tech is how prone it is to errors, noise, decoherence, things like that. And usually, the problem gets worse as you add more qubits, more complexity, more errors. But Google's researchers claim they've flipped that script. They've engineered Willow, programmed it, so the overall error rate actually fell as they increased the number of qubits.
Wow. Okay, so that's not just a small tweak. It sounds like they've actually tackled a fundamental barrier, something that's really held the field back for a long time.
Precisely. Neven himself calls it a major breakthrough. He said it solves a key challenge they've been chasing for, almost 30 years.
Yeah.
He used a neat analogy, actually. Said it's like building an airplane. One engine might work, but 2 engines are safer, 4 engines is yet safer. It's about gaining that stability, that reliability. And even Professor Woodward agreed it was encouraging for everyone trying to build a practical quantum computer.
Right. But it's not quite a silver bullet yet, is it? Even with this progress, there's still a way to go. It's not the complete solution.
No, absolutely. And that's critical context. You have to keep that in mind. Google themselves say this quite clearly. To get to practically useful quantum computers, that error rate needs to drop much, much lower than what Willow showed. So it's a vital step forward, yes. But it's definitely not the final destination.
Okay, so we have Google, led by its chief optimist, calling Willow a major breakthrough, especially on errors. But how are other experts framing this? Is it really this universal leap, or is it maybe a bit more nuanced?
Well, Professor Alan Woodward, who we mentioned, offers a really vital counterpoint. It's crucial for understanding this properly. He warns against overstating things. He says not to compare apples and oranges. His point is that Google chose a benchmark problem that was, in his words, tailor-made for a quantum computer. So demonstrating speed on that specific problem doesn't prove a universal speeding up compared to classical computers. He really emphasizes that quantum computers will be amazing for a range of specific tasks, but they aren't going to replace the classical computers we use every day. They're different tools for different jobs. And keeping that distinction clear is really important when you hear these big claims.
That makes sense. And what about the bigger picture? The global race in quantum. How do people involved in, say, national quantum programs see Willow?
Yeah, that connects to the wider global scene. It's intense. Countries all over are investing heavily. The UK, for example, has its National Quantum Computing Center, the NQCC. Michael Cuthbert, who directs the NQCC, told the BBC he's a bit wary of language that fuels the hype cycle. He acknowledged Willow is a highly impressive piece of work, definitely, but he framed it more as a milestone rather than a breakthrough. Which is interesting, right? It shows how governments and national centers are trying to keep perspective while still pushing forward. He also pointed out the UK's own ecosystem, 50 quantum businesses, 800 million in funding, 1,300 people working in it. It underlines just how competitive this space is internationally.
And Google's specific approach, using superconducting circuits, isn't the only game in town either, is it? There are other ways to build these things.
That's exactly right. The BBC article notes that just recently, researchers from Oxford University and Osaka University in Japan, they published work showing a really low error rate using a different method. Tracked ion qubits. That's a totally different physical system, trapping individual atoms with lasers. And interestingly, their approach can work at room temperature, whereas Google's Willow chip needs those extreme, ultra-low temperatures to function. So yeah, it just highlights the diversity of approaches being explored. No one's sure yet which architecture will ultimately win out or if there will be multiple winners for different tasks.
Good point. And it is important, I think, that Google's scientific results for Willow were published. They appeared in Nature, the journal Nature, that gives it that peer-reviewed academic credibility.
Absolutely. That validation is crucial in science.
So let's try and pull this all together. What does this really mean for you, the listener, trying to make sense of this incredibly complex, but yeah, really exciting field? We've sort of unpacked the huge claims, the technical steps forward, and some expert reality checks on Google's Willow chip.
Yeah, I think the key takeaway is probably this. Useful, large-scale, general-purpose quantum computers, the kind that can solve a wide range of real-world problems. They're still years away, and billions of dollars away, probably. But Willow does represent real significant progress.
Yeah.
Especially in starting to get a handle on that persistent error correction problem. That's huge. It shows scaling might be possible in a way people weren't sure about before. So it's a powerful step, a really important milestone in this global race. But yeah, definitely not the finish line.
Okay. So considering that dual potential we talked about, amazing breakthroughs in medicine, energy, but also real concerns about encryption security and this fierce global race to actually build these machines. What aspects of quantum computing do you think will most profoundly shape our world in the next decade or so? And maybe, how should we as a society start thinking about preparing for when this technology becomes more widespread